Okay, so let's go ahead and get started for today. So we left off last time talking about some proof techniques. We went over direct proofs, proofs by contradiction, proofs by contrapositive. There's a couple. So one thing I want you guys to notice is when we went over the types of proofs, we were essentially proving conditional statements, right? And I told you before that when you're writing a theorem or a statement that has to be proven, you can rewrite it in terms of some implication of some sort, right? So even if it's something like a fact, like I'm saying, like 8 is an even number, I can say, for all numbers that are 8, that number is even, right? And you've seen this in predicate logic, right? This is one of the ways we write predicate logic. Oh, sorry, it's one of the reasons we have predicate logic from propositional, right? We have statements in propositional logic, and we can turn it into predicate logic. And in predicate logic, we can turn these statements into implications very easily. So, one way to see this, I know someone emailed me about this, so here's a good example, right, of the whole 8 is even thing, right? So let's say in propositional logic, I'm saying statement as 8 is even, right? This is a statement. It has a truth and a false value depending on what this is, and depending on the definition of even, right? But let's talk about predicate logic instead, right? I would need a predicate. This wouldn't be a predicate by itself, perhaps, right? Because we needed a variable, right? So maybe I have a predicate of 8, right? Saying x is 8. And maybe I'll say even, say x is even, right? So this would really just say something like this. Right, I've turned this into an implication, right? So in essence, we always want to do some sort of conditional statement, and that's why we had the different techniques that we had last time, right? For each of the techniques that you saw, we were just dealing with conditional, right? What are some different ways to show that P implies Q, right? And the 3 techniques, let's just kind of go over them again. Right? We can just do it directly. Assume P, show that Q is true. We can do this, right? This is the contrapositive, which we know to be logically equivalent with the conditional, right? We assume not P, we assume not Q, and we show not P, right? This is another way to prove the statement. Another way you can do it is prove not P and not Q, right? So these 3 statements are all logically equivalent, right? And so by contradiction, we're assuming this thing inside and showing it has to be false. So what does it mean for this to be false? It means negation of it is true, right? Which is the same as this, right? So these are all logical equivalences that get you to where you want to be. But I also said a few lectures ago that when we're talking about statements we have to prove, it might not just be a conditional, it might be made up of conditionals. So let's just talk about a couple of those cases that you might see, right? And there's really only 2 of them, which are just taking conditionals and kind of making them a little bit extra. Right? So, we have a biconditional, right? These are going to be too involved. It's not something super hard to see. It's going to be pretty obvious. I'm just basically showing you that these are some examples that you'll see going forward, and what you should be thinking about when you want to prove it, right? So we know from logic that the biconditional is really just implication both ways, right? This really says it's this and this going backwards, right? In LaTeX, some of you might already know from doing the homework that this is backslash that applies, and this is just implied by, and you can kind of see why, right? A is implied by B because B implies A, and so on and so forth, right? So as I said, the very first day, LaTeX has some very intuitive naming systems. So let's just look at a quick example of this, right? I'm not going to harp on it too much. You guys know how to prove implications by now. So really, this is just going both ways. I just want to kind of show you an example so you can see how you might want to write these, right? So let's do a theorem that you guys have already seen, kind of both ways. And we'll say that A is even if and only if B squared is even. And we kind of talk about how if and only if is usually the term or the phrase that we use to talk about biconditionals. And sometimes we also use the phrase necessary and sufficient. You won't hear it as much in terms of the theorem itself, but in like when people are naming theorems or they're talking about, oh, we need to prove the necessary and sufficient clause for blah, 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 right? That's what they're talking about. It's really just an if and only if. Just a couple of notational things. Some books will write this as IFF. That's a very common thing you'll see as well. Is IFF to stand for if and only if. So let's say I want to write my proof. All right, here's kind of how it's structured. I kind of reiterated a lot that you should think of this as almost an English class, right? And when you're writing essays, you're usually told, hey, tell people what you're going to do so that they know what to expect. And I've kind of said this as well in terms of some of your writing. So when we write proofs for these, especially if you're about to break it up, right? You're going to do a proof in two parts, one for this direction, one for this direction. Let the reader know what you're going to do, right? I shouldn't have to guess which one you're doing, right? So some people call them the forward and backwards direction, right? And as as you get more used to it, and as you get more familiar with mathematical writing, you can go ahead and just say, oh, okay, in the forward direction, blah, 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 in backward direction, blah, 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 and we're done, right? But for now, since you're just not easing into it, I would prefer to see that you guys are more clear about what you're writing, right? So I can say maybe we will first prove the forward direction. And instead of just saying that, I'll say, in other words, we will show that if A is even, then A squared is even. Right, so essentially that's the forward direction. And by now, you guys know how to do this, right? A is even, there's definition, there exists a k such that A equals to 2k, square that, that's 4k squared, that's equal to 2 times 2k squared, show why 2k squared is an integer, and then so since A squared is 2 times some integer, A squared is also even. And we saw last time, in fact, we saw 3.5 different proofs of why A squared is even implies A is even, right? So I'm not going to go into the details of that. You can refer to the previous lecture if you want to revisit those proofs. But essentially, this is more, I just want to show you what the structure of the proof should look like, right? So we'll first prove the forward direction, right? And then afterwards, I'll just say now we will prove that. You can say backwards or other direction or whatever. So now we'll prove this other words, and then you can restate. You can restate what you're going to prove, right? For people who've done mathematics a lot, you're not going to see them do this, right? It's going to be very obvious what they're trying to prove, but it's good practice to always be able to reiterate what you're trying to prove, right? And so even if you don't write any of these clarifications, I should be able to look at your proof and go, hey, in this section here, what are you trying to show me? Right, and so when starting out, if you don't have this kind of formalism and you don't have this kind of detail, a lot of people will be so stuck on trying to remember how they proved something or how you did a certain technique or a certain trick, and you won't remember like, oh, what was it trying to do here, right? What was the whole point of this? And this is why I always tell you to be as clear to yourself as possible, right? Always write more than you should, if you think it's required. Well, not required, but write more than you should in a way that allows you to have some sort of organizational structure that you can refer to. All right. So that's really all for the biconditional. And just another way you can phrase this, if you really want to, you can say, let's A be the statement is even, right? And then B, the statement that A squared is even. And you can just set this up so you don't have to write these out all the time. You can just say, okay, I'm not going to prove that A if and only if B, right? And it's going to be the exact same thing, but sometimes if you don't want to write out a really long statement, just reference it somewhere, and you can use a letter to symbolize it later on. But at least make sure you clarify what it is somewhere, and you don't have to repeat it over and over again. So this isn't too hard to see, I'm sure. We talked about implications, and so biconditionals are just two implications back and forth. Some people often ask me, is there one direction I should prove first? Well, it doesn't really matter, right? So there's a couple. I've kind of seen this trend where in most textbooks that are introductory, the backwards direction will be almost immediate. Right, and so generally, I'll tell people to get the backwards direction out of the way first, just because it tends to be easier and it tends to be like a one-liner, and the actual proof is forward, right? That's what I care about. Usually, I guess people do this because the forward direction, that's the one you would think to see, and that's the one you would think about the most, and the backwards just, oh, it just happens to be true and gives us a difficulty. But either way, most of the time, one direction will be a lot more trivial than the other. And so if one direction is way easier than the other, do that one first, right? Get it out of the way, and then you can focus on the rest of the proof, right? In cases like these that you just saw, they're both equally important. It doesn't really matter which one I do first. Just make sure you do both, right? But that's just because one of the directions is super easy doesn't mean you should ignore it. So even if one direction is super obvious, you should still state, okay, we'll first prove this direction, but this happens to be obvious because blah, 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 right? So you should still justify it a little bit, and then just leave it at that, right? You should still state that you're going to prove it, but then just, if you want to mention that the proof is short or obvious, you can, as long as you've made some reference to the point that you are, considering that case. You're not just throwing out the window for no reason. There's another type. This is the only other type of thing you'll be asked to prove or that you'll see as a theorem. And I'll call them TFAE proofs or TFAE theorems. This stands for the following are equivalents. And you'll see this a lot in math textbooks. For those of you who have taken linear algebra, this will be very familiar. The invertible matrix theorem is one of the most famous cases of a TFAE. And in fact, for those of you who've done proofs before, that's probably one of the first things you will have to try to prove in terms of TFAE statements, right? So invertible matrix theorem says something like, there's these, if you have an n by n square matrix, then the following are equivalent, and then it lists like 21 different things, right? And some of the important ones talk about, okay, statement, this matrix is invertible, this matrix has linearly independent columns, there exists a unique solution for AX equals B, where A is matrix, blah, 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 right? There's a whole lot of them that we can get, but the point is, what does it mean that, the following are equivalent? Well, it just means logical equivalence. It means if and only if, right? So we talked about how logical equivalence can form tautologies in some way, but really that just means that if I'm talking about logical equivalence being between two statements, I mean that they're either both true at the same time or they're both false at the same time, which is that if and only if, right? So the idea of this is say, I'll say let some conditions be true. right? It doesn't matter what these conditions are. There could be almost no conditions here, or there could be a ton of conditions. But these conditions will all come before, we'll set these conditions into stone before we talk about the statements. So the theorem would say, let some things be true, then the following are equivalent. And this is just a more fancy way of doing if and only ifs, because as you can see, if I just have two statements, that would be an if and only if, right? I could write this as let a be an integer, then the following are equivalent. Statement 1, a is even. Statement 2, a squared is even, right? We've already proven that. But what this format does is it lets us keep going, right? So each one of these would be statements. And to prove this theorem, I want to show that they're all equivalent to each other. Right, so let's draw a quick diagram. Let's say, following that, let's say I have three things. Right. And I want to prove that they're all equivalent. Well, what do I have to prove? Essentially, I want to prove that they're all if and only ifs. So what I need is this. Right. But in an if and only if, we have two arrows going both ways, so we could prove two different things. The question is, do you need to prove 6 things here? Right? And the answer is no. So for instance, let's kind of split these a little bit. Right? So let's pick some directions. Let's say I proved 1 to 2. Let's say I proved 2 to 3. And let's say I proved 3 to 1. Right? Well, look at this. If I started at 1, I can get to 2, and I can get to 3, right? So by going between these two arrows, I get the other one, right? Now, okay, so we can get anywhere from 1. What about 2? Well, we can get to 3, but we can also get to 1, right? Because from 2 to 1, we would just go 3 and then 1, right? And then we're starting at 3, same thing, right? You can kind of see the cyclical logic. If I start at 3, obviously I can go to 1 by the white arrow. But if I want to go to 2, I can just go 1 and then 2, right? So the orange ones are the directions that we get just for free, right? We already have that in the process of proving the other guys, right? So the idea is that we don't have to do all 6. We have to do enough of them so that we can go anywhere we want. Think of this like a roadmap, right? Think of this as you can start in any of these locations and drive to the other ones by following the arrows that you've proven, right? So it's almost like if you've proven one direction or one thing, that gives you a road, right? And then once you have your roads, I can follow these roads to get to the places I want to get to. So you don't have to go to overkill route and prove every single direction. And also, there might be some directions that are easier than the others, right? There might be some very obvious directions that you can start with. And we'll start with those directions, and we'll see what else we need to complete the circuits, right? And so the idea is, whenever you're dealing with something like a TFAE, no matter how many statements you have, start with the easier ones to prove, and usually it'll be fairly obvious which ones are easy, right? We can just read each of them backwards and forwards and think about, how would you prove it? And sometimes it almost arises out of nowhere that, oh, wait, I have a definition for this, or this is just by definition plus some other little theorem and something like that, right? So essentially, you look for those and ask yourself, okay, now that I have this guy going this way, what else do I need to complete this, right? So that's kind of a generalization of the specific case, which is a biconditional. Okay. So that really wasn't very proof intensive. It was just, these are some formats that you'll see for some theorems. They're not any different from the conditional proofs that we've been doing. It just so happens that they are made up of just more conditional statements. Okay? A lot of books at this point talk about disproofs. I'm not going to really touch on that because I think it's almost bad to talk about disproving things as a different kind of proof, right? Because when we disprove something, what we're doing is really we're proving the negation. So this amounts to you being able to take the original statement, write it as a negation like we've done before, right? Write it as quantifiers, then flip all the quantifiers and negate the statement at the end. And once you've done this, prove the statement you've just come up with, right? That's what a disproof is. A lot of people say, oh yeah, you have to think about it as if you want to disprove a for all, you want to pick a counterexample, or you want to disprove it there exists, you have to show that it's true for all things. I mean, those are all true statements, but why are they true statements? That's because of the negation, right? So instead of thinking about disproofs as this other thing we have to learn, I prefer to see it as just, okay, we negate the original statement and then we prove the negation, right? Because if you've proven the negation, the original statement has to be false. In the world that we live in currently, every statement is either true or false, right? We're kind of sticking to that. So since every statement is true or false, well, we either work with that statement or we work with its negation, right? Either way. Now that since I'm talking about negations and sort of disproofs, in terms of problem solving techniques, this problem solving is something we'll talk about as the course goes on, right? And it's something that you guys are going to have to figure out on your own because everyone's going to struggle in different ways and everyone's going to excel in different ways, right? So really, my job here during the lectures is I'll try to give you kind of a widespread of what kinds of problems you'll see, what types of proofs you'll see, some examples of tricks you use to solve certain proofs. But in terms of trying to come up with a way of, how do I say this? In terms of coming up with a way of thinking about problems and thinking about, okay, if I just get a proof in front of me, or if I get a theorem in front of me, what's the first thing I should do to prove it? That's what the homework's for, right? So go through the homework and be honest with yourself. Be honest with yourself in the process and write down, some things you tried to get to your answer, right? It doesn't, the point isn't necessarily about getting the right answer. It's about seeing where your thought process is, right? So if you want, like I said, I'm more than happy to look over your homework solutions and see if they're correct. But if you want to figure out kind of the thought process that should go behind the problem solving methods, I very, very strongly recommend you to keep tabs of what are some things you tried, what are some things you failed at doing, and then keep doing this until you get the answer. And then if you want to come to me on Zoom office hours, or you want to come in person, whatever have you, and to talk about your solutions, we can. And I would much rather see that process that you have rather than just the final answer, right? Because seeing that process can help you say, oh, you might have gotten the right answer, but let's look at the path you took here. Why did you think this way? Maybe we can, maybe there's an issue there that we can solve in terms of why, maybe it took you too long to get to a certain conclusion. We can kind of see if that means there's some underlying issue, right? It's kind of this idea of the actual problem might not be the problem, if that sort of makes sense, right? It's, someone might be doing badly in calculus, not because they're bad at calculus, but because they were bad at trig, right? Or they were bad at algebra, it had nothing to do with calculus, right? There's a lot of things that can go wrong, and just seeing whether or not you get the final answer right or wrong is not a good way of, kind of just troubleshooting, right? We want to look at what the process is, where the process went wrong. And hey, even if you know how to do everything, and even if you know how to get everything right, it's still good to look at what you've done to maybe motivate how you can change your own problem solving process in the future, right? So this is something I'll talk more about more one-on-one, because I think there's a different way to help every one of you, and there's a different way to talk about problem solving methods from your perspective. So I'll leave that more to a meeting thing rather than a lecture thing. But like I said, you're more than welcome to send me an email at any time or contact me, and we can discuss some of these problem-solving methods. You know, I'm not going to ignore problem-solving methods during the lecture. I'm going to give, you know, my general tips like I've been doing and going over what I think you should do to think about a math problem. But some of the nitty-gritty is just things you have to kind of work through on your own the best you can, develop some sort of process for yourself, and then we can talk about that process individually. Okay, so the last thing I want to cover in this whole section, right, this will be the end of section 2, is proof by induction, right? So we briefly talked about this when I gave you that overview of proof techniques. And this is a method of proof. If you're trying to prove a bunch of statements are true when they're indexed on, say, the natural numbers, right? So it's some statement like for every n in the naturals, something is true. So let me reiterate what induction is. For those of you who've seen induction before or know what induction is, and maybe for those of you who are in grad school, there is a more formal way of talking about the principle of mathematical induction. I'll briefly overview this formality, like in a couple of minutes, but really, I'll give you all the general thought process, right? Even with that formality, it's just a way to phrase your answers. It's a different framework within which to talk about your solution, but the flow of the solution should be exactly the same, right? I've had students who've told me they had different classes that talk about induction in completely different ways, and they looked totally different and they got lost. But then when you get to the meat of it, it's really the same thing, right? There's just foreign ideas that you've not seen before that you have to put in. So we've talked about how to create the natural numbers, right? The natural numbers is a set, right? And we'll say it's a set 1, 2, 3, blah, blah, blah. Right. For the purposes of induction, we'll say that natural numbers start at 1. But some people will say it starts at 0 and they'll call it set 0, 1, 2, 3, blah, blah, blah. I mean, that's still fine. 0 plus 1 is 1. This is what we call an inductive set. So I'm not going to go fully into the details about what exactly an inductive set is. For those of you who are interested, we talked about the Zermelo-Fraenkel axioms in set theory. There's an axiom of induction or axiom of infinity, as some people call it. It's very, very strongly related to the method by which we constructed the natural numbers. And you can kind of look up what it means to be an inductive set, right? So turns out the natural numbers are an inductive set. And you know, if you start at any natural number, right? I can start at 10, that's still an inductive set, right? So the idea is we want to start with an inductive set. And we want to show something about which numbers are in the set, so to speak. So what does that mean, right? So I want to prove maybe the theorem that says something like for every n in n, right? P of n is true. Right? And so for example, I can, you know, if I have a theorem that says for every n blah, 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 I can take whatever that statement is and put it into P of n, right? It's a predicate, right? Because it depends on this little n, right? So this just becomes my predicate. I'm saying that's true. Now we can work with this. So the idea is step 1, show that, actually, you know what? Let's do it even more formally. We'll say that, oh, my chalk's running away from me. We'll define S, the set of all n. So let me do it this way. I'll just write in notation form in secular notation. Right, so we'll say S is the set of all things for which this is true. right? Obviously, we want to show that this ends up being all the natural numbers, right? That's the whole point of the theorem. So this would be my proof outline. Right, and remember, this is just a more formal way of doing it, right? Once we start doing some examples, you'll see that it really isn't that scary. This is just me showing some of you who need it, kind of the formalism behind, principle of mathematical induction, right? So we'll create the set S, and let that just be the set of all indexes where this is true, right? So now, step one, if we're showing this for all natural numbers, show that 1 is an S, right? What does this mean? This means show P of 1 is true. Well, what's the second step? Show that, show that K in S implies K plus 1 is an S. Right. So for those of you who might remember, the first time I talked about this, we had that kind of ladder metaphor. That's what I'm doing here, right? I'm climbing the ladder. So this is just showing PK implies PK plus 1. Right. So K, if we're doing it formally, we would say that K is greater than or equal to this number over here. Wherever we start, we pick a number greater than that, right? But we were essentially saying that if K is an S, then K plus 1 is an S. And the idea is from the set theoretical axioms, right? We've done something with constructing the natural numbers successively, right? We say something with plus 1. Well, that kind of shows here that I can go from 1 plus 1 is 2 plus 1 is 3. And we've said that's kind of how we constructed the natural numbers, right? The natural numbers are constructed by starting at 1, going to 2, going to 3, ad nauseum, right? We keep going up to forever. So what this means is we combine those two, right? We have a starting point and we have a successor function. And the fact that this is an inductive set tells us by the PMI, right, which is the principle of mathematical induction. That's how people, you'll see the statement a lot, right? By the principle of mathematical induction, those two statements tell us that S is equal to the natural numbers, right? Because if the 1 is an S, then number 2 tells us 2 should be an S, 3 should be an S, and this will keep going all the way for all of the natural numbers. So that gives us that this set S has to be the natural numbers. But S was defined as all natural numbers where P of n is true, right? But then by how we define S, this means that P of n is true for all n, which is what we want, right? That's the idea. And so you can kind of see what I talked about last time in here in terms of the kind of roadmap of how we prove things by induction. This is our base case, and this is our inductive step. And like I said earlier, this is just our formalism for this. You'll sometimes see this in books, especially older math books, which want to be very strict on how they present mathematical induction. And you'll see this kind of thing where you take the set to be the set of all indices where the statement is true, and then you somehow show what that set is. And once you know what the set is, you say, oh, by the principle of mathematical induction, this is true for all of these guys, right? But in reality, no one really does this anymore, right? I mean, people still do this, but you don't have to, right? As long as you've somehow shown that you've conclusively done a base case and an inductive case, that's enough, right? So let's kind of write down an outline of what we have to do, right? So step 1, prove the base case. The base case is the smallest step. Right? This is the smallest value needed, right? Now step 2. Write down what the inductive hypothesis is. Right? And in other words, this says that for all k, and so let's call the smallest value, let's call it n0, right? Actually, I should make a note of this. In mathematical notation, for those of you who are not used to it, we use symbols to represent ideas and concepts, right? And oftentimes we use letters. Usually when we index, we use subscripts to represent, oh, this is an index to delineate different versions of this, right? So if I have a sequence, I'll usually use a subscript to denote where in the sequence it is. I'll use n1, n2, n3, right? Usually 0, for those of you who've done physics, 0 indicates a starting point, right? So generally you use a 0 as a subscript to say, okay, this is just some constant, right? This is just some number that's specific, and that's, tells you it's not arbitrary, right? Sometimes people will use indices to tell you what variable it's related to, right? So for example, if I pick a number, and you'll see this later in row analysis, but if I'm saying, okay, you give me a number, call it x, right? If you give me x, and I use this x to pick another number, let's call it n, sometimes you'll see that as nx, right? It's n depending on x, right? So sometimes you can see these subscripts as depending on. But again, that's just notation, right? If you're never sure of why someone uses a certain notation, they're allowed to define the notation however they want, as long as it's defined somewhere. We do have standard notations that you've seen me use and that you should try to develop. If at any point you have questions on, hey, why do we happen to use this letter for this, or why do we use this for that as standard notation? Sometimes it's just, well, that's how it was. But I'll try my best to explain, what are some reasons why they came to it, because obviously it's not like there's no rhyme or reason to anything, right? We have reasons that we picked certain things to use. But anyway, we'll call this n0. The statement is true for that value of k. And in the same note as earlier, right? This we'll be saying P of n0 is true, and here we'll be saying that P of k is true, right? In terms of the statements that we said earlier, right? Taking the entire mathematical formula and saying, okay, let's call the statement P, right? That's what we're referring to. And in step 3, so here we didn't prove anything. We just wrote down our hypothesis, right? It's saying that, okay, we're going to assume that this is true for this k, right? You pick fix a k, right? This is not everything at once. It's just you pick one, you pick an arbitrary one, not a specific one. You pick an arbitrary k, but fix it to be greater than n0, and show that no matter where I picked it, the next one is also true. So prove this is true for k plus 1. And the whole idea of induction, and this will have to use the induction hypothesis. Right, so this is typically called the inductive step. This is where we're proving the implication that P of k implies P of k plus 1. And this almost always uses the induction hypothesis. And it's a bit obvious now, right? I mean, when I say, okay, you're obviously going to use the previous step, and that always makes sense. But this is something a lot of people forget and get stuck on when trying to prove something by induction, right? You have to kind of carefully see and ask yourself, have I used the inductive step? A lot of people get stuck on induction, right? It seems like there's too many things to do. It's not clear what the next step is to get to my right answer. And the solution to that is always make sure you use your inductive step. The inductive step will generally make it very easy to see what you need to do to finish the solution. And we'll see this in a few examples, right? So the rest of today, I'm just going to do maybe 2 or 3 examples of induction, right? And we'll follow these steps. And once you've proven this, step 4, you just write down very nicely and just the conclusion very nicely and say, oh, by the PMI we're done, right? Because we are done. Right, so you can end this with some statement that, okay, so thus by the principle of mathematical induction, we have thus proven the original statement is true, for instance. Right, so these are all steps. Okay, now that we have our steps, let's prove a few statements, right? So example 1. Prove that the sum of the first n odd integer numbers, right? I'll call them positive integers, is n squared, right? So, and maybe usually before you even start, maybe you see why it's true, right? It's part of what the base case is, but you can see like, what does this mean? Well, what's the first one? The first odd integers, 1, 3, 5, 7, 9, and so on, right? So 1 by itself is just 1. 1 plus 3 is 4. Well, there's 2 of them. 2 squared is 4. 1 plus 3 plus 5 is 4 plus 5, which is 9. Well, that's 3 squared. Plus 7 is 16, that's 4 squared, and so on and so forth. So you can kind of see that you expect that to be true. But we have to prove it, right? So let's look at these steps, right? And so on the board here, I'm showing you, like, I'm writing it out as step 1, step 2, step 3, so we can refer to this. But in your proof, try to avoid doing that, right? Try to just write these, as a paragraph. You can split it up in different paragraphs. Say, okay, here's the base case, here's the inductive hypothesis, here's the inductive step, or something like that. But don't say like step 1. I'm just doing this to refer back here. But I'll say, okay, so for the base case, where do we start? Well, this is just saying the n positive integers, right? Where maybe I should have probably said that. Prove that for all n, right? So what's the first natural number? Well, in this class, it's going to be 1, right? We're going to define the natural number as starting at 1. So we'll say n0 equals 1. And keep it with that notation, right? It's n0. Okay. Well, there's only one first positive integer. 1 is equal to 1 squared, right? That's done. That's it. So we've proven the base case. And it really is this simple most of the time. You just write it down, and it turns out to be very obvious. And usually the first number you check is either 0 or 1, which are very easy numbers to work with, right? So it shouldn't be surprising that the base case is usually like immediate, right? Like before you even start the proof, you probably already see that the base case is true. That's always pretty easy. So step 2, assume that for all k greater than or equal to n0, right? The sum of the first k odd positive integers is k squared. Right, so all I've done here is I've written down the inductive hypothesis, right? For all fixed k, I have that p of k is true. Finally, step 3, I want to prove that it's true for k plus 1, using this same k, whatever k I just used, right? So I'm going to write this. So I could write a sum in summation notation, and I'll use summation notation in the next proof. But I want to avoid all the nasty indexing of like, making like 2k plus 1 or 2n plus 1 or something like that. So we'll just keep it in this because this won't be too hard to see, right? So let's call this, thing, right? Sum of the first n positive integers let's call this sum n. It's like a predicate of some sort, right? So this thing, right? This statement says sum k equals to k squared, right? So here we want to ask ourselves, what do we want? We want to prove, or we want to show that sum of k plus 1 is equal to k plus 1 squared. And that's what we want to show. Now, a lot of people get stuck here because they're like, wait, I need to prove this equality, and they start working with this. But the whole idea is, I'm only allowed to work with this from the definition. So I always think about it as the left side of this thing I'm trying to show comes from just how we define this. Whereas the right side will come from taking this and adding on information that we get from the inductive hypothesis. And that's what I mean by use the inductive hypothesis. So let's see what this means, right? We start on the left. What is the sum of the first k plus 1 integers? Well, this is just odd integers. That's just what it is, right? But how else can we rewrite it? Well, you want to ask yourself, what do we know? The inductive hypothesis tells us we know something about the first k integers. I know something about sum k. So let me write this in terms of sum k, right? So what is this? It's really the k plus 1th odd integer plus sum k, right? And this is sum k plus 1. But what's the difference between each odd integer? It's just 2, right? How do I get from one odd integer to the next? I just add 2, right? So here, I just have, so I already know what sum k is. I'm adding the next one, right? So this just becomes k plus 2, right? So whatever this, I guess, let's see. Oh, I guess it wouldn't be, right? So for example, what, you want to think about what number that is, you kind of have to think of it as, okay, since this is an odd number, we have this 2k plus 1. So this almost comes from the definition, right? So if this is my index, what's my actual number, right? With the first odd number is 1, and then we have 3, 5, 7, 9, and so on, right? So you can almost see that if we chose to index at 1 less, you get 2 times 0 plus 1 is 1, 2 times 1 plus 1 is 3, 2 times 2 plus 1 is 5, and so on and so forth. So we have this sort of k plus 1 thing going on, or rather 2k plus 1. And so the k plus 1th odd integer is just 2k plus 1, right? Where k now doesn't represent the index of the integer, but it represents an actual number, right? This is now 2k plus 1, right, by the definition. And then what's sum k? Well, this is where we use the inductive hypothesis, right? And so here, we would say this is because of the inductive hypothesis, right? This is where I use it. I'm converting sum k into k squared, right? But then now I can recognize that, if you factor this, this really is just k plus 1 squared. So I've proven that sum of k plus 1 is k plus 1 squared, right? So that's how you would do that. If you want to see if you want to see something more formal for this, let's let this be the index of which kth odd integer. Oh, I'm sorry, you can't see this. This is off the screen. Let me maybe write it over here. So what I mean by that is, so let's choose an index, right? And this is the actual number. So this is the first, second, third, fourth, fifth odd number, and so on. The first odd number integer is 1, 3, 5, 7, 9. One way you can see this is how we get from here to here, or you can multiply by 2 and subtract 1, right? So 1 times 2 is 2, minus 1 is 1, 2 times 2 is 4, you get 3. 3 times 2 is 6, you get 5. 4 times 2 is 8, you get 7, and so on and so forth, right? So the k, so I can almost say, let me do it in orange over here. The k odd number is 2k minus 1, right? So the k plus 1 is, well, just put k plus 1 in over here. Is 2 times k plus 1 minus 1. Distribute that. That's 2k plus 2 minus 1, which is 2k plus 1, right? So that's how I got this, in case you were not following what I was saying earlier, especially because I was writing off screen. Okay? But then now that we've proved this, we've proven the inductive step. So now all we have to say from here on forward is, by the principle of mathematical induction, we're done, right? We've proven that for every n, the sum of the first n odd numbers is n squared. Right? Okay. Moving on. Let's look at summation notation. Right, and you'll see this a lot. For those of you who might need a refresher or haven't seen summation notation before, this is the capital Greek sigma. I'll usually have an index here. In this case, I'll just say like n. Maybe I'll put a number up here, right? We index, for summation notation, we index on the natural numbers, right? So if I say something like this, right? This means I have a formula, right? And wherever I see an n, I'm going to plug in the value here, but I'm going to keep adding it, right? So S for sum. So this means we're adding up all the values of this guy for n equals 0 all the way up to n equals 3. So this is really just 3 times 0 plus 3 times 1 plus 3 times 2 plus 3 times 3, right? That's one way we make notation easier. And I could also replace this with infinity. And this just means add it up to infinity, right? I keep going on and on and on. And when we use infinity, we call these series, right? Some of you, most of you have heard that term before. But here we're not going to be dealing with infinite series. We're going to be dealing with finite series. And keep in mind that an infinite series sometimes can't be proven by induction, right? Induction only works up to an arbitrary natural number. That might not be infinity, right? That you have to be very careful on where you quote unquote stop your induction. Proving a statement is true for all natural numbers is not the same as proving it's true for infinity. Even though there's an infinite number of natural numbers, right? So that's something we have to be very careful of. Anyway, so we can start with this. Let's see. Okay. So here's another exercise. Prove that for all natural numbers, right, the sum, and here I'm just going to use I as my index. So I from 0 to n of I times factorial is equal to, let's see, what is it? I think it's factorial. And for those of you who need a refresher or don't quite remember it, a factorial is just, for example, 5 factorial is 5 times 4 times 3 times 3 times 4, right? It's, you know, in the case of integers, sorry, in the case of natural numbers, the factorial is just you multiply, you start with that integer or natural number and you keep multiplying down until you get to 1. And by definition, 0 factorial is equal to 1. And this just by definition. For those of you who've seen some statistics before or probability theory, the factorial is just a specific case of what we call the gamma function, right? If you've seen the gamma function before, it's defined recursively, but if you put a positive integer into gamma function, you get factorials. That's all it is. Okay, so we need to prove this statement. So what's step 1? right? So for the base case, we're going to look at n equals to 1, or rather n0 equals to 1, right? So what does this become? This becomes the sum I equals 0 up to 1 of I times I factorial, which is equal to, let's see, 0 times 0 factorial plus 1 times 1 factorial. Or 0 times 1, well, remember 0 factorial is 1, 0 times 1 is 0, 1 times 1 is 1, so this is just 1. So we just did the left-hand side. So sometimes I'll denote this as LHS for left-hand side. What about the right-hand side? Let's do it. So we've got 1 plus 1 factorial minus 1. This is 2 factorial minus 1, which is 2 minus 1, which is 1. And since the left-hand side and the right-hand side are the same, we're done with our base case. Right. In the interest of space, I'm going to erase this now, right? So that we can start with denoting what our inductive hypothesis is. But again, as you can see, the base case is always pretty easy, right? It's either you do it directly, or you just compute the left-hand side, compute the right-hand side, show they're equal, right? It's really not that bad. So now, for the inductive hypothesis, right, we'll assume that for all k greater than 1, or fixed k, right? And we want to now show that it's true for k plus 1. So now, step 3, I want my inductive step. So what I want to do is I want to say we want to prove the statement for k plus 1. So what is the statement? It's this. Right, notice I could have written k plus 2, but I didn't. I wanted specifically just plugging in k plus 1 into our original equation, right? We want to kind of keep it in this format. Before I continue, I guess I just realized one thing I should note is I'm being kind of informal when I just keep saying for all k greater than 1. What I really mean is in this particular case, I'm fixing a k, right? I'm saying that for no matter what k I pick, I'm just picking one of them. No matter what singular k I pick, this statement is true, and in using that, the next one is true, right? It's only one rung of that ladder I talked about, a couple lectures ago, right? I originally thought I was going to do this as a separate section after I was done induction, but now that I'm thinking about it, I don't think I should. But so I just want to let you guys know there's something called strong induction, and it's no different than regular induction. But strong induction, instead of just saying this is true, you still have a for all in there, but you're essentially saying it's true for all steps. So not only, so you pick a k, right? You fix it just like you did here, and then you say the statement is true for k minus 1, for k minus 2, all the way down to n0, right? So that's strong induction. And why would you need this? Well, there are some times when if you just assume this statement is true, that's not enough to prove this statement. Maybe you need more than that. And there's cases like recursion, right? Like, for example, some of you might have heard the Fibonacci sequence, right? It's I start with 1 and 1, and then I take two previous terms and add them together. So, for instance, if I start with these two, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on and so forth. That's the famous Fibonacci sequence. And you can prove something about ratios of every term divided by the previous term, right? And this becomes what's known as golden ratio. But when we're proving stuff about this by induction, we have to use strong induction in the sense that we don't just need one previous step, we might need two previous steps because each term depends on two previous terms, right? I'll give you an example of this on the homework when I do the homework on induction, But and if you have any questions on that, let me know. But I want to at least tell you that whenever you see strong induction, it's not necessarily doing anything differently or doing anything in a way that's more complicated than regular induction. It just means that you might need more steps. In regular induction like this, some people call it weak induction, right? You see this case, we only use this one k, right? We're not saying that it's true for k and k minus 1 and k minus 2. We're just saying that p of k implies p of k plus 1. So the main difference is in weak induction, we have p of k implies p of k plus 1, right? Whereas with strong induction, we have p of 1 and p of 2 and all the way to p of k. All of those together imply p of k plus 1, right? But if you think about it in the ladder metaphor, there's no difference, right? I still need my base case, I still need to step on the ladder, and I can keep going all the way up until I'm where I want to be, right? I can keep climbing the ladder. If this is confusing to you, don't worry too much about it. It's not super important, in my opinion, at least at this level of mathematics. Just know the idea of how induction works, right? And then just recognize that you might need more than it. Like if just this doesn't work, include more, right? If just the k version doesn't work, you can assume it's true for k minus 1 and do it there. You can assume it's true for k minus 2 and do it there as well, and so on and so forth, right? Because the idea is for fixed natural number k, if I had it for a base case, I can prove a certain number of them gets you the next one. You can start with multiple base cases, right? So in the case for strong induction, we have multiple conditions, right? So for example, if I have 3 conditions, I need 3 base cases, because those are the things I need to get to the next one. And then you can move them up in chunks, right? So just to get back to this is what we want to prove. And again, let's start with the left-hand side, right? We start with the left-hand side, we write this out by definition, and somehow turn it into something we're familiar with, and then we'll use our induction hypothesis. So when we start on the left, this sum is almost what we want. It's just an extra term, right? But when I'm adding a bunch of terms, remember what we had in the previous case with the odd number. I just took everything from the previous one, and what do I have to add on? Well, let's find out, right? I can start with this sum, right? The sum of the first k plus 1 terms obviously includes the sum of the first k term. I didn't just come up with this from nowhere. I wrote this down because I knew we would need it because of this guy. Well, what's left? What's left is just to add the k plus 1's term, right? Well, let's write down what the k plus 1's term is. It's just plugging k plus 1 into I over here. So this is plus k plus 1 times k plus 1 factorial, right? Now, let's use the induction hypothesis. Sometimes I'll include that above the equal sign just for convenience, right? But here, recognize that, okay, the whole point of induction is now that we've written it like this, we know what this is equal to. We are assuming it's equal to that. So this is equal to k plus 1 factorial, sorry, it's up here, minus 1, plus this. Right? And I guess, we can kind of shift my terms around, move the minus sign over here. I'll notice that there's a factor of k plus 1, right? Factorial. So I have k plus 1 factorial, right? This is equal to 1 times k plus 1 factorial, right? Anything times 1 is itself. And there's a factor of k plus 1 over here, right? So it's 1 plus k plus 1 times k plus 1 factorial minus 1, right? So those of you who might want to see this algebraically, just convince yourself, call this x, right? And if this is x, this is x, right? So 1x plus k plus 1x is k plus 1x, right? So here's my x, right? Okay, well, what's k plus 1 plus 1? That's k plus 2. But what's k plus 2 times k plus 1 factorial? Well, k plus 1 factorial is multiplying k plus 1 k all the way down to 0, right? Or rather, all the way down to 1. Well, k plus 2 is the next term. So this is just k plus 2 factorial. But what's k plus 2 factorial? It's just this thing, right? K plus 1 plus 1. So that's what I wanted at the end of the day, right? So then I go on to say that, okay, now by the principle of mathematical induction, we have proven our original statement, and we're done. So notice how the format, even though it's a different, completely different problem, the format is almost, a carbon copy of the previous format that we did for the first problem. We'll notice that I started by writing out the left side. I thought about what is this by definition? How do I write this in a form where we can use some previous information? So I wrote this out. I wrote it out, right? I replaced that previous information with what we know, or I used what we know. So I used an induction hypothesis. And then from there, I did some algebra to get to what I want. Let's say you didn't know what all this stuff was, right, in the middle. One way you can do that, problem solve, is this should be your final answer. You know what you want to prove. So start here at the end and go, okay, this is k plus 2. I don't have any 2's in here. I just have k plus 1. How can I write k plus 2 factorial as something with a bunch of k plus 1 factorials? Well, k plus 2 factorial is k plus 2 times k plus 1 factorial. So we go from here to here, and you can say, okay, the minus 1 matches with the minus 1 here. How can I write this guy as this other thing? And then from there, maybe you'll see that it factors out, right? So it's not too bad to see. But the main idea is it really follows the same format. The key is this step, using the induction hypothesis. One thing I'll mention is sometimes for induction, your arguments will look almost exactly the same, and that's to be expected. For factorials, this is almost always going to be what you do. So whenever you see a factorial that you're trying to prove somehow, or you're trying to prove something about factorials and sums of factorials by induction, you're almost always going to have this case where you pull out the next term times the previous one factorial. And you can probably see why, right? It's because of this induction thing where we are moving one step forward. Okay. I've got 2 more examples that I think will be good to see. So one thing you'll see a lot for induction is factorials. Another one you'll see is exponents. So maybe we'll say that, prove that for every n we have, oh, wrong color. Where's my white chalk? There it is. For every n we have 2 to the n is less than or equal to 2 to the n plus 1 minus 2 to the n minus 1. It looks like we've got a bunch of stuff here, right? So again, we're going to do the same thing. Step 1, base case. Right. So 2 to the 1 is on the left side. On the right side, we have 2 to the 1 plus 1 minus 2 to the 1 minus 1 minus 1. That's equal to 2 squared minus 2 to the 0 minus 1. Right? That's 4 minus 1 minus 1. That's 2. Well, 2 is less than or equal to 2, so our base case is done. All right. So we're good there. Okay. So once again, for convenience, I'm just going to get rid of this. Base case isn't important. It's just there to set our foot on the ladder. So now I'll say step 2. All k greater than 1. Let's assume that 2 to the k is less than or equal to 2 to the k plus 1 minus 2 to the k minus 1 minus 1. Okay? So what do we want to prove? We want to show, and by the way, I'll always use WTS to stand for want to show. It's a common abbreviation in math. You will see it in some books as well. Here I'm just being lazy, but that's what that means, want to show. We want to show that 2 to the k plus 1 is less than or equal to 2 to the k plus 1 minus 2 to the k plus 1 minus 1. Right? We want to show that this statement is true for the next step, right? So the first thing we want to do is, again, start from the left-hand side and see how we can rewrite it as something we know about. So we know that 2 to the k plus 1, if I want to write this in terms of 2 to the k, well, what is something to the power of something? Like, for example, what's 2 cubed? 2 cubed is 2 times 2 times 2. I'm multiplying the 2 by itself 3 times. So here I'm multiplying the 2 by itself k plus 1 times, right? But this is just 2 times 2 to the k, right? So now I have this 2 to the k out here, right? Okay, so now I've rewritten this in a form that I've seen before. Now I can use the induction hypothesis. I'm using this statement, right? I can keep the 2, but if 2 to the k is less than this guy, I can put this guy in here, right? This is less than 2 times 2 to the k plus 1 minus 2 to the k minus 1 minus 1, right? Well, let's multiply this up. Instead of, when we put these two together, I'm moving this one step above. This becomes 2 to the k plus 2, right? Or even better, if I'm just recognizing that I'm moving this up by 1, I can rewrite it as 2 to the k plus 1, right? Here, I'm adding 1. This is k plus 1 minus 1, right? I'm adding the 1 to this k, right? I'm just rewriting that, right? I could have said this was 2 to the k, but I'm rewriting it this way to kind of match this. And finally, I have minus 2. Well, this isn't quite what we want, but we don't need anything fancy to get exactly what we want, right? All I need is for this to be less than this. But if I have a positive number subtracting 2, well, clearly, if I add 1, it's going to be bigger, right? So clearly, this is going to be less than or equal to 2 to the k plus 1 plus 1 minus 2 to the k plus 1 minus 1 minus 1. I just want it to be a minus 1. It doesn't matter, right? So there you have it. This is exactly the inequality that we wanted up here. And so, by the principle of mathematical induction, we've proven our original statement, right? Nothing more to say about that. And so just like for the factorial version, right? In the factorial, I told you there's a common trick of just pulling out the last term. When you see exponents like this is pretty much always going to happen, right? And you can see why. We need the next term, so you'll see often that we'll just pull off a factor and get the term before that we can use from our induction hypothesis. Right? I'll say maybe this is because, so this step going from here to here is because of the induction hypothesis, right? So that's really not that bad. And what I'm doing here is I'm giving you, I'll give you one more after this, but I'm giving you different types of problems where you can see that the actual algebra involved is different, but the tricks are really the same, right? It's the same process of I'm rewriting it in terms of something we know. And then once I know something about this, I'll use the induction hypothesis to get to the next step. Okay. So the final one I want to do is something that, we know we're doing induction. So let me show you maybe how can we see this from, something not a bit more complicated, but something that we want to write as a more compound statement. So I have more conditions now, right? Saying that as long as, for all n, for all x in the reals where x is greater than -1, or I could have, so this, I could have just said for all x in maybe 1 to 3, that's fine as well. I just wrote it that way. But if I write this in interval form, I know that this is the real numbers, right? Intervals belong to real numbers. I have this statement, right? So essentially, what I want to do is, since I want to prove this for all n and n tells me this should be an induction. So that means I'm performing induction on this statement. What I just underlined, that's my P, right? That's my P of n, right? So what this tells me is wherever I have this, I can assume that x is greater than -1, because that's my condition, right? I have this, I want to prove that statement, right? So this is just kind of recognize whenever you see the n and n, or rather n in the natural numbers, you know that you want to work with induction. So you then rewrite the statement as how you want it and then move forward, right? And then from there, everything's just the same. I just want to show you something that's not just, one single quantifier, even though there's two quantifiers, this is fine. And here, maybe the order matters, right? In this case, the order doesn't matter. When you have two for alls, the order doesn't matter. But sometimes if you have for all and there exists for all, we've seen already that the order does matter, right? And so as long as this statement is true and this statement is true, it doesn't matter what order we put them in. So even if I had given you the order separately, right, I could have said for all x in this, prove for all n in n, 1 plus x to the n is greater than 1 plus x. You can still do this by induction by recognizing that this is still a for all. So we can flip these two and then now remove this and just do induction the rest of it, right? So we're almost like changing the way in which that works. And maybe it would have been better to like show that to you at the start, but that's fine. You get the idea. So what's the first step? Base case, right? And there's two variables here. Notice there are two variables here. You're always inducting on n, the natural numbers, right? So you want to be clear what your induction is on. So in step 1, the base case with n0 equals 1, so if 1 plus x, the 1 is greater than equal to 1 plus 1 times x, right? But this just says 1 plus x is greater than equal to 1 plus x, which is perfectly fine, right? That's obviously true. And again, a lot of times when you plug in a 1, it becomes a very obvious statement, like it's an inequality, but it just happens to be equality, right? If you want to be sure, you can ask yourself, okay, can I prove that this is true if n equals 2? And you go, okay, this is 1 plus x squared greater than equal to 1 plus 2x. And it turns out this guy is x squared plus 2x plus 1. And this is positive, so this is greater than this. Fine, you can do that just to convince yourself. But even if the base case looks really, really dumb, like stupid easy, like it doesn't matter. You just need the base case to be true. It doesn't matter how easy the base case is to prove. Even if it's way harder to prove it's true for n equals 2 or n equals 3 than n equals 1, it doesn't make the proof any different. You can still just use n equals 1 because the meat of induction, right, is the inductive hypothesis. That's what you're trying to prove. Okay? So again, base case, we're just going to get rid of it. It's easy to see, especially for n equals 0 or n equals 1. So now we're going to write down for step 2. Again, we're going to do the same thing, right? For all k greater than 1, assume. Sorry, I should maybe write it this way, right? So we'll assume that for k greater than 1, I have 1 plus x to the k is greater than equal to 1 plus kx. Right. So for step 3, what I want to prove is I want to show that this is true for the k plus 1 case. Right. So we want to show that 1 plus x is greater than equal to the power of k plus 1 is greater than equal to 1 plus k plus 1 times x, right? And again, here we have this hidden condition of, right? And I'm not going to reiterate it. It turns out this is just here to make these look nice so that nothing weird happens in our inequalities. And we'll see why, right? But just imagine I have this statement throughout the entire thing, right? My condition of x is it's always greater than -1. And we'll see why that's used. Okay, so this is what we want to prove. So again, let's start on the left side. Again, we're just going to find a way to turn this into the previous one. And we've talked about exponents, right? How do we get exponents to look like what they did before? We take one term out. Right, so now I know what this looks like. By the induction hypothesis, I know that this thing is greater than that thing. And here's why we need to be careful about where x is. This is greater than, right? It matters because I want this thing to be positive, this thing on the inside. The whole thing hinges on 1 plus x being positive. Because if 1 plus x is negative, this would have to be flipped because it will start having negative terms. That's why we have to be careful. But since x is greater than -1, that's what allows us to do this, right? So we do this, and I'll say that this is because of the inductive hypothesis, and also that x is greater than -1. Therefore, 1 plus x is greater than 0, and this is greater than 0, and everything works, right? Okay, so I got this, and I want to turn it into what? I want to turn it into this, right? So this is almost like, you can almost sort of see this as I'm getting ready to pull something out, right? So let's see. So maybe I can expand this. This is 1 plus x plus 2 plus 1x plus x squared, right? But look, this, hold on, I might have, oh, sorry, I meant, yeah, that's why, okay, that's why I'm confused. I kind of did this extra step in my head ahead of time. Right, so when I FOIL this out, I just get 1x, kx, and kx squared, right? Well, I have a 1 plus x, kx, I can combine these two, right? So this is what I was trying to do in my head. I'm ahead of myself. Right? Well, I've got 1 plus k plus 1x, which is what I have here. That's what I want to show, right? This term's clearly positive, correct? Because it's an x squared. X squared is always positive. K I picked to be some natural number greater than 1. So this is clearly just greater than this part. Right, that's all I need. I can just get rid of this guy. Right? So there you have it. I already showed what I wanted to show. And so, once again, by the principle of mathematical induction, we're done. And so the key here is to notice that, you know, I said something yesterday about make sure you use all the conditions. If you weren't sure where we use this condition, that's when you want to take a closer look at, was I actually able to do all my inequalities, right? So because you have to be very careful when you're dealing with variables. Because when you're dealing with variables, we might not always be able to do these inequalities, right? It's like, I'm sure a lot of you have seen in pop math the whole like, oh, how do we prove 1 plus 1, sorry, how do we prove 1 equals 2? You start with like a equals b, you turn into like a squared minus b squared, and you start doing some stuff to it. Well, the problem there is a and b were variables, and at one point you would divide by 0, right? Same thing here is when we are essentially moving from here to here as an inequality, this inequality only holds if this other term is positive, right? Because otherwise we'd flip. Because when you're dividing by a negative, you flip the inequality. So we have to be very careful about that condition. But that's what allows us to do this, right? Notice how inequalities are always going to go the same way, right? If at any point in a series of equalities and inequalities, if you end up flipping 2 of them, you're not going to get something, right? Because if I want to show that 1 is greater than 2, which is, sorry, 1 is less than 2, which is greater than -1, that doesn't really help you with anything, right? You're only showing this statement is true and this statement is true. It doesn't connect this and this in any way, right? So when you're writing a series of equalities and inequalities, they should only ever be going in the same direction. And that's kind of the direction we want, so we're fine, right? But you want to make sure that you don't have anything flipping, because then it's no longer true. Okay? So I've kind of like done a lot of different examples for induction, just because usually people take a bit longer to get used to how to do induction, because you get so many different types of problems. But my whole point in doing this is, notice I did the exact same thing every time, right? I did the same thing where I start on the left hand. I did my base case. I wrote down my induction hypothesis. I started on the left side. I figured out how to rewrite it as something we have seen before from the inductive hypothesis from step 2. I did the induction hypothesis. I used that fact, and then I just simplify it until I get what I want. And sometimes writing out what you want to show, you know, that is that kind of same idea of, you know, write what the last step should be, right? It tells you by looking at this what you should get to, right? And that's kind of how we want to look at this. So that wraps up this section. That wraps up section 2. We're done with the section that introduces proofs. So I don't know when I'll write it, but I'll be writing your take-home test at some point this coming week. So let's see. There'll be so I won't give a quiz in this section, but I will give that take-home test in this section. It'll cover logic. So be prepared to do stuff like negations. Be prepared to convert statements in both predicate and propositional logic. Maybe you might expect one. I won't like do too many truth tables because they're a bit fussy, but I'll expect at least 1 or 2, maybe probably just 1 truth table, and then I'll give you a few proofs that are going to be similar or a bit harder than the stuff you'll see in the whole books. All right. So that's all I have for today, and then next Monday we will start up with functions, right? So we all know what functions are. We've talked about functions in high school. We've used them a lot. Basically all of math. We talk about functions in high school, in middle school, whatever. But we haven't really defined what a function is other than very vaguely, right? So people say these terms like, oh, it passes the vertical line test, or maybe there's some verbal way we can describe what a function should look like, or something like that. But there's a more formal way to define it. And before we do that, we have to talk about relations, right? So that's where we start on Monday. We'll talk about relations, then we'll talk about functions, and then we'll go from there. And then we'll talk about maybe different types of functions. What are some ways we can have different definitions for types of functions, and that will give us the baseline that we need to discuss more of mathematics. And that's all for today.